Thank you very much for that introduction. Um, the presentation I'm going to show you is by Chris Burn and myself. Like Dave said, I've been working with Chris Burn since 1997, and we have gone out in the summer and winter to make field observations in the Western Arctic. We both like to travel by snow machine and in summer by boat. We have been studying permafrost conditions and how they've been changing so often that we collect temperature readings from pipes like these that go down 50 meters or so in the ground. And the next slide is a map of the Western Arctic coast where we've done most of our traveling. On the map you can see Herschel Island and the Mackenzie Delta area. In this presentation I'm going to show some data from Herschel, from Esagok, the lake on Richards Island that Ross Mackay drained in 1978, and also from near the east branch of the Mackenzie River. I know this area because I've been traveling there all my life, and Chris and I have been lucky because we have not yet got stuck anywhere we didn't want to be. Chris has been known to get his snow machine stuck, but I've always got him out in 5 minutes or less. The only times he has been caught in overflow was when I was not with him. So that's his fault, not mine. In the spring, we traveled to Herschel by snow machine. We have done it in 10 hours from Inuvik. It's no small feat. That's just about 300 kilometers in one day. Chris was really sore that night, and in the next few days we were able to travel around, and in 2009 we saw many of these pieces of blue glacier ice that had been frozen in. This was the first time I'd seen glacier ice near the coast, and I think it probably came from those ice islands that are breaking up. Anyway, I want to talk to you today about 3 sets of information from our region. All of them are about how the landscape is changing in the Western Arctic. First, I'm going to show you some landslides that happened in the fall of 2009. These came after 2 really wet months. Then I'm going to talk about ground temperatures in permafrost and what is making them change. Finally, I'm going to show you some information about changes to the active layer. The last part will follow up measurements that Ross Mackay began in the 1980s. But before we do that, I'm going to give you some background on climate change in the region. This slide shows you the mean annual temperature in the Delta as it was measured first in Aklavik and now at Inuvik. The measurements began in 1926, and the line is the running mean of 10 years data. You can see that since about 1970, the climate has warmed up. In the first part of the period, the mean temperature was about minus 9.5, and now it's about minus 7.5. This change in temperature is measured everywhere in the Western Arctic, all along the coast and in the Delta. The warming we are experiencing is really noticeable in the fall and winter. This year, the river has only just gotten ice cover, and it will be a few weeks before we can go out in the Delta. The top graph on this slide shows how the warming throughout the year is firmly tied to changes in winter conditions. The bottom graph is of summer temperatures and the year-round conditions. The summer temperatures are not the same each year, but these changes don't significantly affect the annual temperature. The climate warming has led to changes in permafrost temperatures. These maps were made by Dr. Ross Mackay and Chris and Steve Coquel. Ross's map is from 1970, and the update shows that the ground has warmed throughout our region. It has warmed near the ground surface by between 1 and 2 degrees. On the map you can see Esagok, which I'm going to mention later, and also the Caribou Hills. Another aspect of the climate is precipitation. We get about a third of our precipitation as rainfall in the summer. It comes especially in August and September. This year it was just wet most of the time. It never really poured, but everywhere the polygons were filled up with water, both in the troughs and in the low basins. The measurements for rainfall don't have a trend over the last 50 years, but have just varied from year to year. This means that we have to use probability when we test for rainfall effects, but before I talk about that, one of those effects, I'd like you to look at the record of total precipitation, not just the rainfall. This slide is the total precipitation measured at Inuvik since records began in 1958. The total precipitation is the rainfall and the snowfall. You can see that the total precipitation measured since 2002 is less than what was recorded before then. You will remember on the last slide that the rainfall has not changed, so these data indicate that the snowfall is now less than before. I don't think anyone in Inuvik thinks there's less snow now than there was before. It is interesting that this change of snowfall happened when the weather station moved. I'm not going to say much more about snowfall, partly because of this. Anyways, what I do want to tell you about is what I saw on September 20th, 2009, when I was going hunting on the East Branch of the Mackenzie. We had a very rainy 2 months, and then I could not go out for 3 days in mid-September because it was just pouring. The storm gave us 27 millimeters of rain, and when the rain stopped, I went out, and along the Caribou Hills, there were 8 landslides I could see from the river. Many of them came right down to the river. They were brown mud. They were almost all south of Reindeer Station. I had been on the river a week before and had not seen them. And Chris had not seen them when he came back from Ilisarvik at the end of August. Some of the landslides did not make it to the river and piled up on the hill slopes. They have now been colonized by vegetation, and it's not easy to see them anymore. But in total, there are over 25 separate features that we could see on the Google Earth. Some are quite small, and all of them are new. These landslides were due to climate warming because of the summer of 2009. Were not due to climate warming because of the summer of 2009, and it was relatively cool with a mean temperature of 10.7 Celsius between June and August, ranking below 40th of the 56 years of records at Inuvik. But the 45 millimeter rainfall in September and 131 millimeter when September and August are counted together are each the highest on record. That storm between the 17th and 19th of September was the second biggest event recorded for all Septembers. In this diagram, we have ranked the rainfall for September and August and plotted it as a probability. The probability is across the bottom and the rainfalls are on the side. There are 56 points, and the line to summarize them has been fitted by eye. The 2009 point is way above the line, and if we bring it along to the line, then it fits at about once in 500 years level. At the moment, we must regard these landslides as due to extreme weather rather than climate change, because there is no trend in the rainfall. This makes it difficult to predict when more landslides might occur. The highways crews on the Dempster have the same sort of problem to deal with as with this flow that happened in shale just near the bottom of Ogilvie Hill. This picture was taken in 2011, but in 2010 the highway was closed for several days while they cleared debris from here and from near the Ogilvie River. Now I'm going to switch to ground temperatures and go to Herschel Island. There is not much snow on most of Herschel Island because of the vegetation is very low. Instead, the snow piles up in gullies and at the coast. In 2003, we made a set of 10 stations up the hill near the settlement. The site number 5 is in a small valley and gets covered with lots of snow, but the others are blown clear. We put a data logger that records the temperature near the top of permafrost at each position. In the summer, the data logger boxes are visible. Several of the sites have given us data in most years since 2003, but not all of them. The boxes that are very low to the ground tell us when freezing begins because we have used when the temperature inside the box stays below 0 throughout the day to mark this. This slide shows you the annual temperature at the top of the permafrost at site number 7, and also readings from one of the pipes we have near the top of the hill. The measurements of mean annual ground temperature are from about 15 meters depth. You can see that both sets of the measurements have increased, but the near surface readings swing around more than the temperature at 15 meters depth. The change from year to year is up 2.5 degrees at the top of the ground. It is much less deeper down. This shows how different the changes can be in the top of the ground and the value of several years' measurements to show a real trend. The data do show warming of the permafrost, but you can take your pick by how much. There is a difference on the hill slope in the temperatures due to the snow cover. The slide shows the temperatures at 3 points over a year. The deep snow site is number 5, is the warmest in winter, and it takes the longest to freeze. The year-to-year difference in temperature depends on how much snow comes on a site, how cold it is, and on how long the freeze back takes. Last year we had a cold fall and everything froze up quickly, and then there was lots of time for cooling. This year it's really warm. It's colder here in Yellowknife than it is in Inuvik. So we have looked at how the temperature of permafrost changes in winter conditions. This graph shows the change in winter conditions shown as freezing degree days with the change in annual temperature of permafrost. You will expect that colder winter gives a lower annual temperature. This is what happens, but we can't do anything about the winter weather, so we have to adapt. The next slide shows the same annual temperatures in permafrost and the length of time it took for freeze up of the active layer. You can see there's a good fit here. We can control a freeze up by clearing snow. Then we looked at the same graphs for the other sites with many years' data. You can see that at each place there was a strong fit between the length of freeze up and the annual temperature. So it seems to us that the landscape is signaling how we can keep the permafrost cold, especially where there's infrastructure we want to protect. It seems to be telling us to work on helping the freeze back to be quick. I'm now going to turn to Ilisarvik and talk about the active layer. Ross Mackay drained Ilisarvik back in 1978, and it has been a research site since then. This year it was really wet in the lake bed. Usually there are 1 or 2 ponds, but not as many as you can see on the slide. There is an active layer course at Ilisarvik in the tundra. It has 12 sites, and they run from this lake up to the hill. We measured the thaw depth in the course at 12 sites at the end of August each year. Ross set up the active layer course in 1983, and the record is continuous since then. The ground along the course has lots of hummocks, so we have to measure in the center of the hummocks where the active layer is thickest. In this slide, you can see that the dowels were stuck into the ground, and the top of them shows you the shape of the active layer. The ground is quite rough on the hill slope. When I first started coming to Ilisarvik in 1997, there were only a few small alders on the hill slope, but now there are lots, and some are over 1 meter high. The slope was a smooth gradient, but now there are lots of tussocks, and it's quite bumpy up the slope. The active layer course runs from the lowland near two lakes up the hill to the upland. I'm going to talk about three sets of sites: the ones at the top of the hill, the ones on the slope, and the ones on the lowland. The hilltop is about 16 meters above the bottom of the line, and the top and bottom sites always have about the same amount of snow because it depends on the vegetation. But on the slope, the snow depth varies, especially at site 6 and at the bottom of the hill. So I'm not going to talk much about that place. This is the graph of the average active layer thickness over the whole record. You can see that the active layer has got thicker, and on the average rate has given about 7.5 centimeters since 1983. This is the longest record in the Western Arctic. Some years it was really deep, as in 1998 when we had a very warm winter and early spring. We are now getting to the 1998 depths as the regular readings. It is interesting that when we split the sites up into uplands and slope, we get different patterns of active layer change. The rate of active layer increase is not the same, and the pattern for variation each year is different. They both have increased over time, but in different ways. The upland has had more deepening than the slope. We have not shown the lowland here, but it is close to the upland behavior. You may remember that earlier I showed how different seasons are contributing to the climate change, and we have found that the climate change of the seasons doesn't show up in the same way in the active layer. On the slide you can see where the crosses are that there is a fit between the seasonal change and the year's thaw depth. You will notice how the upland and lowland are affected by the fall weather of the year before. This is just like the temperature information I gave you from Herschel. The slope is only responsive to the summer. One of the things that is different between the slope and the upland is the ice content of the permafrost. If there is a lot of excess ice, then energy can create subsidence, not active layer deepening. At Esagok, the upland and lowland have very high water contents in the permafrost, which is on the right side, but the water contents in the upland is high because of the top of permafrost is that black muck. It is full of organic material. It doesn't have much excess ice when it thaws without a load. On the slope, the water content seems to be lower, but as you can see on the left, there's lots of excess ice. On the hill slope, the water drains away when the ice melts and the ground subsides. In the flatter ground, the water freezes in the fall, and the thawing in the next year starts from the same ice content. This is why the long-term trend is so much better in the flatlands, because each year the starting conditions are the same. The settlement on the slopes is becoming really noticeable. In the last couple of years, we have really begun to see the ice wedges on the hill slopes stand out. Ross used to tell us about these in the 1990s, but now they are really clear for us to see. They are standing out because of the settlement. The ice wedges are pure ice, so above them, the active layer doesn't get thicker, just the ice melts. Here is one of the bigger troughs on the side hill. The wedges are really wide because of the way that wedges grow on the top when the top is being eroded. We have been measuring the settlement of this trough since 1996, when Chris put some benchmarks in with my friend Alex Alanik. In the middle of the trough is going down slowly, and the edges are also moving into the gap. On the active layer course, there are two ice wedges between sites 8 and 9. The troughs began to appear in about 2005, but we only noticed the lower one this year. As I told you earlier, the slope used to be smooth, but now the troughs have gone down by about 50 centimeters. The troughs are wet because of the depression, and the alders are coming into them. This increases the snow depth at these sites, and so the amount of thaw. When Chris left Ilisarvik this August, he saw more ice wedge troughs in upland ground than he can remember. Usually we see the polygons nicely develop in lake basins, but now we see them everywhere on the tundra. They show us how difficult it is going to be to use the land until the top 5 or 6 meters of permafrost is melted. Chris and I enjoy traveling together, and we've enjoyed being with Rossamackide, Gary Island, Ilisarvik, and Paulatuk. We hope you have enjoyed listening to some of these long-term observations. They are the scientist's way of telling the story. Thank you.